So the first thing that we're going to start in on chapter 3 is solving systems of equations. And when you start systems of equations, it's kind of important to know what exactly a system of equations is. So what is a system of equations? We can answer that by saying it is two or more equations graphed on the same set or on the same coordinate plane. Okay, so basically when we have two lines or three lines, but we'll mostly deal with two lines, you want to basically see where they cross each other. So two or more graphs or two or more equations graphed on the same coordinate plane. The solution to a system of equations is the point or points where the lines cross each other, also known as intersecting. Okay, so here's three quick examples of three different types of solution sets. So if you look at the first one, this is the typical one that we have, and that is where they cross and strike each other at one point of intersection. Now think of them as like roads. So these roads have one street where they, or one point corner where they cross each other. So that would be one coordinate or one set of coordinates. These two right here, when the lines are parallel, if the roads are never going to run into each other, the lines never cross each other. So there's 0 points of intersection. And then the third one is when the lines actually are the same line. So we need to write down a few more things about these. If they cross at one point, like the first case. So in this case, there's one solution. We would say that these graphs are consistent because they do have an answer. But because they only have one solution, that one solution is what we call an independent solution. And I'll talk more about a dependent solution in a minute. So when you have one solution, it's consistent and independent. The next set, the parallel lines, since these never cross each other, there's no solutions. So you would look for parallel slope or the same slope. And these would be inconsistent. If they're inconsistent, they're not going to be dependent or independent. And then lastly, this last set, because you can't see that there really truly are two lines, we would say that these have infinitely many solutions. Clearly, if there is a solution, that makes them consistent. But when the lines are identical, that means that the solutions are independent. Or sorry, dependent. I wrote down the right thing, said the wrong thing. And you always want to make sure that your equations are in slope-intercept form, because that gives you the ability to compare slopes and compare their y-intercepts. Okay, so we're going to practice some of these and see where that gets us. Basically, we're going to be graphing two lines on the same graph, and that's it. Okay, this one's nice. It's already set up for you in slope-intercept form, so you just have to graph them and see where they cross. So let's go ahead and graph them. Hit pause, graph each line. So I'm going to graph the first one, starting at -8, up 1 and down. Now, you guys doing this with pencil makes it a little bit easier so that you can see exactly where they're going to cross each other. So mine might be off just a smidge. And then my other one starts at 1, and it goes down and right, down and right. I probably should have done a better job continuing my line. If I stop too short, I may not see where they cross. So it looks like these two are crossing each other at the point 3, -5. So this means that these are consistent and independent. All right, let's move on to graphing this one. So this one starts at -2 and goes down 3, 1, 2, 3 over 1, down 3 over 1, or up 3 left, and so on. Okay, the other line starts at +3 and goes up and left. Oh, and we just landed on our point. So down and right. So I don't need to do a whole bunch there. And I can see that it should have landed at -2, +4, if I'm not mistaken. So again, that makes it consistent and independent. Okay. All right, so this next one says your equation is 6 equals -x minus 3y. So we have to do a little rearranging. So down here at the bottom, I'm going to take that -3y, I'm going to add my x to the other side, so I get x plus 6, and then I'm going to divide everything by the -3. So that first equation is y equals -1/3 x minus 2. We need to graph that one. So it starts at -2, and then it goes down 1, right 3, or up 1, left 3. Then the other equation was x plus 18 plus 3y equals 0. Again, let's do a little rearranging, but on this one, let's move the y to the other side, since that would only take one step, and divide by -3 here, and you get y equals -1/3 x minus 6. So just comparing the slopes, you can see that these two have an identical slope, but they have a different y-intercept. So when I go do my line on this one starts at -6, but it's never going to run into the other one. And we should have known that already because we checked our slope. So right away, I know that this one has no solution. And therefore, it's inconsistent. Okay, so why don't you? Okay, so I want you to try the next one by yourself. Hit pause and then come back and check it with my answers. So I'm going to start this one right here. So I took the first equation, which was x plus 2y equals 4, and I rearranged it below the problem or below the graph, and I went ahead and graphed that. Now, I'm about to graph the other one, which is already in slope-intercept form. And if you notice, these two are the same exact thing. So if I go to graph it, that green line would sit right on top of the blue line, because they have an identical slope and an identical y-intercept. That means that these have infinitely many solutions, not infinite solutions. So they have infinitely many solutions, which makes them consistent and dependent. Okay? This next one, you have two lines, one of which is y equals -7. So that should be pretty easy. We have a horizontal line at -7. The one before that says x plus 3y equals -15. So if we go to rearrange that, we get 3y equals -x minus 15. And again, you're going to divide by 3. You get y equals -1/3 x minus 5. So graphing that one, we have a -5 y-intercept and a slope of -1/3. So it's crossing that horizontal line at the point 6, -7. It has to be somewhere with -7 because the y values for the other one are only -7. So 6, -7 is your solution, making it consistent and independent. So if it crosses at one point, don't forget to list what point that solution is. Okay? Last one, this one you have to rearrange both. So again, I want you to pause it, do it on your own, and then check back. Check back after you do the first equation, and then check back after the second equation. So I'll do the first one, and I want you to double check yours after just the first one. So I just rearranged the first equation, and after reducing and everything, I got my first equation is y equals -3/8 x minus 3/2. So not a very pleasant y-intercept for us to graph. Now hit pause again, do the other one, and then we'll go ahead and graph that. Okay, so I rearranged the second one, put the x's on the other side, then divided by 32. The first fraction was -12/32, so I divided both of those by 4. And the 48/32, I divided both of those by 16. So now comparing them, you can see that both your equations are identical. We do have to graph them, but we at least know we only have to graph this ugliness one time. So we're going to go to -1.5 on the y-intercept, okay? And here's where you got to be a little bit careful. So you're going to go down 3 steps. So you're always at a half mark. Down 1, 2, 3 puts me between -4 and -5. And then you have to go to the right, 1, 2, 3, 4, 5, 6, 7, 8. So you're at 8, -4.5. And so we know in this particular case that they are consistent and dependent, and there are infinitely many solutions. All right, last one. Candy is sold by the ounce at 2 stands at the mall. One stand charges $1.50 per ounce. So we know that this one's going to be 1.5 per ounce, so it's going to be times X. A second stand charges $6 for the jar, and you can fill that jar for 75 cents per ounce. So you got your $6 for the jar and 75 cents per ounce. Okay. So what you need to do is you need to plug in some values so that you can graph this line. I know, for instance, if I look at the red equation, if I buy nothing, it's gonna cost me nothing. But if I buy 2 ounces, I'm just gonna get a 2. That's gonna cost me $3. If I buy 4 ounces, it's gonna cost me $6. If I buy 6 ounces, it's gonna cost me $9. And that gives me a line right there. On the other one, however, I'm going to pay $6. In theory, even if I bought nothing, I'd pay $6 if I want the jar. And then from there, it's going to go up 75 cents per ounce. So, $6.75 for 1 ounce, $7.50 for 2. So let's try to drop a point there. So $7.50 for 2. And then it would take me up 75 cents every time. So you need to find where this is going to cross the other one. Why don't we plug in like 6 as a test point? Because 6 gave us a nice one for the other. So let's do 6 plus 0.75 times 6 and see what that gets us, and see if perhaps that's where they're going to cross each other. So 75 cents times 6 is going to give you $4.50 plus your $6. So you're already at $10.50. Okay, so I want you to find where these are going to cross each other. That looks pretty crappy on here because it almost looks like they cross there, but that red line's a little bit off because you can see right here that 6 for the $1.50 one is only going to cost $9. So let's fix this a little bit. Okay, so I want you to maybe make a table of values and see where that's going to cross each other. Okay. I'm going to redraw this. So I want you guys to, do some guessing and checking, set up a table, maybe set them equal to each other and see where they're going to cross each other and answer the last 2 questions. Because I am almost out of time because I can't make a video longer than what this one is. So we'll talk about this in class and finish it up together.